We're going to be talking about heating curves. This is just a reminder. This is an image you've already seen of the thermodynamics of phase changes. And what's important is that converting a solid to a liquid is endothermic, and converting a liquid to a gas is also endothermic. And so heat is required for those processes to occur. And also remember that we can cause phase changes by either heating or cooling. So we're going to talk about heating curves, but at the end we're also going to talk about cooling curves. So the exercise you did in lab was to create the heating curve for water. And so you took ice and you filled it with water, and mostly that was just so that the thermometer could get an accurate temperature reading. So you started with a mixture of ice and water, and then you put it on a hot plate and applied constant heat, and that converted the solid into the liquid. And then you increased the temperature of that liquid until it started boiling. And there you also have two phases present. You have both the liquid and the gas. So what you created in lab probably looks something like this. And we're going to talk a little bit more about heating curves, not only the heating curve that you generated, but also general heating curves and how they are a little bit different than the one you have. So here's a heating curve that's something like you generated. And at the beginning you had ice, and of course you had some water that you mixed in so that the thermometer was in contact with the water. And you put it on a hot plate and you started heating it. During this flat part, you had both phases present. You had ice and liquid water present in the beaker during that whole flat part. Once you got to the end of the flat part, then that signified that all of the ice was then converted into the liquid, and it's still on the hot plate. You're still going to heat it. You had pure liquid during this entire increased slope, so that signifies the temperature of the liquid is increasing. And then at the top of that slope is where the water began to boil, and you see the presence of the liquid and the vapor together. Those would stay together during the entire flat part at the end. Two other parts of this graph that are important are the 0-degree line and the 100-degree line. The flat parts are both related to the freezing point and the boiling point of water, which you should have been familiar with already. Now, your heating curve is actually just a smaller portion of a larger curve, which is what I'm trying to show you here. It's either temperature versus heat added, or it can be temperature versus time, assuming that heat is added continuously. So the curve you generated is only part of the entire curve. We're going to talk about general heating curves now. So this would be the entire curve. So if we think about a general heating curve, it is always temperature on the y-axis. The x-axis is either heat added, or it can be time if heat is being added at a constant rate. At the very beginning of the curve, before you've added any heat, at the lowest possible temperature, you have the pure solid. Since it's a heating curve, you need a heat source like a Bunsen burner. You have only solid at that initial sloped line, and the increase in slope, it signifies that the temperature of the solid is increasing. At the end of that sloped line is where the solid begins to melt. And you have solid and liquid present in the same beaker, and that is true throughout that flat portion of the curve. That I'm showing you there. So that entire flat part, you have solid and liquid present together. That line represents melting. At the end of the flat part, you have 100% liquid, and that's true during the entire sloped portion that follows. So we're still heating the liquid, and so the heat being added along the x-axis goes into a temperature increase along the y-axis. and the temperature of the liquid will increase until you get to the boiling point, at which point the substance will begin to boil and you will have both the liquid and the vapor present together. And we're still heating it, but here the line is flat because the heat being added along X does not go into a temperature increase, but rather goes into a phase change, the phase change of vaporization. So that whole flat part, you have liquid and vapor present. At the end of the flat part, you've converted all the liquid into vapor. And you can see that all we have left is the gas. And then the temperature will rise again once we have 100% pure vapor. The heat that goes in will go into increasing the temperature of the vapor. And we're going to erase everything and just reiterate a couple of things that I mentioned, but I want to write them down in words. The sloped parts always indicate temperature increases. So the heat being added is causing the temperature to rise. That is only true when you have pure phases present. You would calculate the heat Q using the equation Q equals mc delta T, which is the same equation you used last semester when you did calorimetry problems. Q is heat, m is the mass of the substance, C is the specific heat of the substance, which you would be given, and delta T, of course, is the change in temperature, the final temperature minus the initial temperature. Where the temperature does not increase but stays constant in spite of heat being added, those represent phase changes. So the flat parts represent where the heat being added is causing a change in phase. The first one on the left is melting, and the second one on the right is vaporization. These are both endothermic phase changes, which means heat has to go in, which means the delta H, or heat of fusion, and the heat of vaporization are both important parts of the calculation for the Q, the heat involved. That's the next thing I want to talk about. When you're doing calculations involving heating substances and how much heat is involved, it's best to approach those by thinking about the segments of those heating curves and then just add the Q's all together. You have to calculate them separately. And so here you see a full heating curve. So the most number of segments you may have in a problem is 5, but it could just be a portion of the curve. So it might just be sections 2, 3, and 4, or it might be all 5, might be 1, 2, and 3, might be just 1 and 2. Depends on the substance that you start with. So you use substance segment 1 if you're increasing the temperature of a solid. The mass and the specific heat would be those of the solid. The second segment, you would use the moles of substance times the heat of fusion, and that would be the heat required to convert the solid to the liquid. The third segment is again Q equals mc delta T. The mass is the same, but the specific heat of the liquid will be different than the specific heat of the solid. Another point worth making is that delta T for that middle segment, the third segment, if you're going all the way from the beginning of that segment to the end, the change in temperature is definitely going to be the boiling point minus the freezing point, because remember, the liquid only exists between the freezing point and the boiling point. So those two values are important in these calculations. You need to know what those are. The fourth segment, you're causing vaporization, so the heat would be calculated using moles and the heat of vaporization, which would be given to you. And the last segment is again Q equals mc delta T. The mass will be the same, but the specific heat will be different for the gas than it was for the liquid or the solid. This is the heating curve for water. So if we look at the important parts of this curve, the numbers are significant now because we have a specific substance in mind. So 0 is the freezing point of water, 0 degrees, and 100 is the boiling point of water, 100 degrees Celsius. Also, the length of the lines is relevant. The length of the vaporization line is much longer than the length of the fusion line, and that's because it requires more heat to boil, to vaporize a sample of water than it does to freeze the same sample of water. More heat is required. you can see the numbers at the top that are relevant. These numbers at the top would refer to this process, each segment for 1 mole of water. Now, since you can have a heating curve, you can also have a cooling curve. So cooling curve would be temperature versus either heat removed or time if heat is removed at a constant rate. The difference is here that you start with the gas, because that's what is present at high temperature before you've removed any heat. The temperature will fall, and at the bottom part you will have gas and liquid together. You'll still have a flat part, which would refer to condensation. So the heat being removed goes into the condensation process. At the end of that flat part, you again have liquid. You'll have pure liquid during that whole sloped part, where the temperature of the liquid will fall as you remove heat at a constant rate. And the bottom of that line, you will have some solid and liquid together. And so that flat part represents the freezing process. As you continually remove heat, the liquid will freeze and turn into the solid. And at the end of the flat part, you will have 100% solid. And then the temperature will continue to fall, and as the temperature of the solid decreases.